The observable universe hosts a vast array of complex systems across many different fields of interest. These can be modeled using theories that use a layer of abstraction to separate the complexity from the fundamental nature of the individual interactions. Describing complex systems as systems of oscillators may sound obscure, but in a strange convenience, it describes in a generative way all sorts of physical systems, and not just in the context of standard classical and quantum harmonics. As examples, there are lots of physical, chemical, biological, and even social systems that can be reduced to populations of harmonic and anharmonic oscillators. The heartbeat, for example, is just a collection of oscillating heart cells that a wave propagates on. And synchronizing neurons in the brain are oscillators as well, and have been treated with these methods to give a rich understanding of the kinds of patterns that we see experimentally. Rather than just simply observing and recording the patterns in such reductionist systems, abstract generative models must be constructed if we are to enrich our understanding beyond simply measuring outputs from abstract models. In higher level modeling, we can say that ensembles of globally coupled systems of oscillators can manifest in a synchronization into the appearance of a macroscopic mean field. In this mean field theory, an ensemble of particles, highly coupled through entanglement, for example, can give rise to a scalar field, or a scalar field can itself mediate a strong coupling between ensembles of particles. Both views happen to be equivalent, and we have what we call a duality of description. Natural systems of synchronized particles can also form macroscopic mean fields, such as atoms in Bose-Einstein condensates or electrons in superconductors, where we have integer multiples of the individual particles and quasi-particles. In these condensates of bosons, we see spontaneous breaking of symmetry of the condensate, where it does not matter if one adds a particle or subtracts it from the condensate itself. A mechanism which may appear odd in terms of charge transfer, but in terms of representing this in terms of momentum, it appears obvious, such as in the quantum Newton's cradle model. The core reason why we have the separation of the different nodes in an ensemble of integer particles is down to the uncertainty principle, and in condensates of bosons, this is the cause of the separations that we see. Quite often, clusters of synchronized elements are observed in between the regions of the unsynchronized elements. In a type 2 superconductor, for example, we see an intermediate phase of ordinary conductivity by unsynchronized electrons mixed with the superconductivity mediated by the synchronization of electrons in the Cooper pairs, which are a quasi-particle. This effectively means that we have a mixture of a synchronous condensate with asynchronous individual charge carriers at intermediate temperature and fields above the synchronization phases. Synchronicity and asynchronicity might seem dichotomous conditions of a functioning system, yet both states can in fact exist simultaneously and durably within a system of oscillators in what is called a chimera state. Chimera states are patterns where synchronous and asynchronous domains coexist, taking its name from the composite creature in Greek mythology. According to the myth, the main power of the chimera is that the closer someone gets to it, as they are pursuing it, the further away it is from you in actuality. This has an ironic resonance with the chimeras we are talking about in the context of systems of quantum oscillators and chaos theory. The exotic state still holds a lot of mystery, but its fundamental nature offers potential in understanding the governing dynamics across many scientific fields. Of particular interest in this work is the effect symmetries of a complex system can have on the emergence of chimera states. For example, the effect of having the same versus different coupling strengths of the outer regions of the mean field to the center regions can cause a breaking in the symmetry of synchronization. This drives the system to adapt and perform a kind of emergent error correction or annealing. Such annealing can occur in systems of harmonic oscillators, both classical and quantum. Chimera states are therefore an integral part of any emergent complex adaptive system. Such systems can be used to simulate other complex systems with equivalent behavior and can be used to solve optimization problems. In machine learning techniques, for example, several optimization problems can be represented as paths or logical decision trees, which themselves can be reduced to the Boolean satisfiability problem, or SAT problem. Basically, it's an algebraic or Boolean logic expression that looks like the following equation. Think of, for example, trying to find on a map the shortest path to take on foot from one part of a city to another. If you wanted to do a brute force search, you'd be trying every single possibility that existed. Or perhaps you're studying protein folding and you need to fold in the minimum energy configuration so that you can understand how proteins interact with viruses or the general way in which protein denaturing works. Now, in these scenarios, you might also realize that nature doesn't trend towards the global minimum energy configuration, and asynchronous effects have to be considered with the synchronous effects, so we're already entering the territory, so to speak, of the chimera. Another example is the knapsack problem, where you have a bunch of items, but you can only carry a certain amount. Suppose you're working for NASA and you're building a rocket, and you're trying to figure out how much fuel to put into the rocket, but remember that fuel adds weight. So what are the optimal fuel to payload ratios? What's the value of each item versus its weight, where there are n objects with weights w and values v? Because these are optimization problems, the notion of solution is not entirely adequate. Backtracking is rather designed for decision problems, in which one should answer questions of the type, is there a feasible solution, or is there a feasible solution achieving a value of least v? In this case, the extension of a solution might again be a solution itself. These are all massive problems, with tons of simulated parameters, but the common goal is to maximize the value of the object selected, respecting a limit w, the weight, on the sum of weights of the selected objects. In the design of a quantum network, the adiabatic theorem can be primarily used to solve the Boolean satisfiability problem, such as the clique network problem, a clique being a complete subgraph of a total graph. The size of a clique is the number of vertices it contains. The clique problem is the optimization problem of finding a clique of a maximum size in a graph. For this we use the adiabatic Hamiltonian, where the solutions are the maxima and minima in terms of a graph, where there is a collection of nodes in a grid. This graph is analogous to a program in an adiabatic quantum computation, where the initial state of qubits are connected in a certain way in a network. As a side note, it so happens that even though adiabatic annealers and gate-based quantum computation are vastly different paradigms, the Wigner-Jordan transformation allows one to map fermionic problems onto an Ising spin model. The spin model can, of course, be implemented on an annealer, or through the use of the variational quantum algorithm, can be implemented on a gate-based quantum computer. The annealing part of the variational quantum algorithm comes from using classical machine learning and network synchronization to find the parameters of the gates that minimize the ground state of the Ising Hamiltonian. One thing that it is easy for the adiabatic quantum computation to do is quantum error correction. The adiabatic theorem tells you that the longer you wait for your system to reach its final state, the more likely you are to have stayed in the ground state, or, said another way, the less likely you are to have excitations, which basically translate to errors. Therefore, in order to reduce the error, all you need to do is run the algorithm in the adiabatic quantum computation for a longer time. If you ran it for t equals to infinity, you would be 100% accurate. Mapping a problem to a Boolean satisfiability problem can be difficult, or can create added work in the translation. Imagine a problem that requires the number of qubits to scale with the number of real variables by a polynomial of high degree, or even worse, exponentially. You might also find that an approximate solver is not good when you have hard constraints that must not be violated. These machines also operate at finite timescale, therefore there is always some noise in the adiabatic quantum computer. Therefore, it is key to understand how such systems work with a mixture of synchronized and unsynchronized states to understand our chimera state for any given system in effect. These chimera states can form naturally in systems that can be treated as systems of oscillators, like the quantum systems that we've discussed. This is really the main reason why quantum systems should be considered applicable for solving these types of problems, Boolean stat problems, in the first place in a quantum computer framework. As we've seen in a previous video, the quantum systems themselves can be very sensitive to initial conditions and can create chaos, even in controlled or isolated quantum systems. However, we see from looking at the mixture of asynchronous and synchronous elements in the chimera states and how they are in fact beneficial to driving an adiabatic quantum computing network to achieve quantum error correction, but at the same time allowing for it to behave as a metaheuristic system, so that we never have the system becoming trapped in solutions corresponding to local minima, which are not the globally optimized solution to the problem. So in effect, our chimeras really offer the best signature for the quantum computation we are interested in using for solving the kinds of problems we may want a quantum network to solve. But what does a chimera state in a quantum system or network even look like? It turns out that a quantum system's response to the presence of a chimera state is a sharp transition at a critical value of a variable p, above which percolation occurs, but below which it doesn't occur. Near this critical value, the system is very sensitive to minor perturbations, and a number of intriguing phenomena, such as the formation of self-similar fractal patterns, can be observed, as we talked about in our discussion of chaotic systems in the context of quantum mechanics. These self-similar fractal patterns are found to take place at or near this transition point, which are called critical behaviors or percolation thresholds. Many complex systems, including biological and physical networks, are considered to be utilizing such critical behaviors for their self-organizing and information processing purposes. For example, there is a conjecture that animal nervous systems tend to be dynamically maintaining these critical states in their neural systems in order to maximize their sensitivity to response and in order to have information processing capabilities. Such self-organized criticality in natural systems has been a fundamental research topic in complex system science and relates intimately to the study of percolation thresholds, with these percolation thresholds corresponding themselves to chimera states. The chimera states are then said to be the metastable medium, or the discontinuous path coupling between a stable coupling regime and a disordered state in a network. Moreover, the link between the percolation dynamics of complex networks has not been lost on those that employ statistics in the analysis of such networks, such as the utilization of renormalization group theory, a technique straight from the quantum field theory toolkit, which is sometimes used to quantify the percolation thresholds of complex systems as a percentage. It's remarkable how self-similar dynamics of percolation thresholds can be applied to different areas of study, from monitoring the organization of groups of insects, the synchronization of signaling neurons in the brain, to the aspects of finance, or the dynamics of how forest fires spread through the topology of an uneven landscape, all of which have chimera states hidden deep within the statistics. Even more astonishing is how to appreciate just how much the underlying factor of what we have flippantly referred to as the randomization term work with the power laws that emerge from a coupling. The somewhat invisible flow of randomization is really what drives these systems that we've talked about to emergent equilibrium, critical behaviors, and towards the self-similar, self-organizing configurations. The true origin of randomization we know absolutely nothing about, the consequences of which has shaped the dynamism of the universe across and in between all possible limits. Not taking this amazement for granted, we may have to think about the emergent nonlinear behavior and dynamics of the real world as merely an echo of the balance of synchronization and chaos that exist in the quantum mechanical foundations of the whole universe. The echo of the chimera that happens to emerge into our reality.